An Introduction to Recursion. In this video, I will explain mathematical recursion. What is recursion? Recursion is a technique to solving a problem by defining a mathematical or programming function that references itself over and over again until a certain criteria is met. An answer is obtained by passing smaller and smaller pieces of a problem to a defined function. One way to visualize recursion is to imagine a 3D printer that prints other 3D printers. In this picture, you will see that the large printer is able to print a smaller printer, and that smaller printer is able to print an even smaller printer, and so on and so forth. In this analogy, our printer is a mathematical function which makes smaller and smaller duplicates of itself to solve a problem. The analogy is not quite perfect, but it's a good visual starting point to understand what recursion is. To understand recursion, we must first start with functions. In mathematics and in computer science, functions are indispensable to solving problems. A simple way to think of functions is to think of them as boxes. On one side of the box takes input. The box then takes that input, runs some logic or transformation to it, and then spits out an output on the other side of the box. Now let's talk about the factorial. We will learn about the factorial in order to better understand recursion. In math, the factorial of an integer is the product of all the lower positive integers up to that number. So for example, the factorial of 4 is 4 times 3 times 2 times 1. So we multiply the number itself times all the non-negative integers before it, in this case 3, 2, and 1. Another example is the factorial of 5. And the factorial of 5 is 5 times 4 times 3 times 2 times 1, which is equal to 120. Now let's go back to the function and relate it to the factorial. As I mentioned, the function is like a box that takes input, processes that input, and produces an output. We can define the factorial calculation as a function. For example, if we call this box here the factorial function and give it an input value of 5, the factorial function will produce an output of 120. Now that we have a general idea of what a factorial is and what a function is, let's create a factorial function that uses recursion, that is, a recursive function. Since we're talking about recursion, we're going to implement the factorial as a recursive function. A recursive function is a certain type of function that calls itself in order to solve a problem. But before we create our recursive function, we should first talk about what a recursive function is, what a recursive function is made of. There are 4 elements to a recursive function. The first element is the function name and its input parameter or variables. The parameters are placeholder labels for our input. The second element of a recursive function are the calculations or logic which will be applied to the input in order to create the output. Calculations are not necessarily have to be mathematical operations, but most of the time they are mathematical operations. The third element of a recursive function is the recursive call. The recursive call is unique only to recursive functions. Recursive calls are only possible if we have a function name. The last component of a recursive function is the stop and continue conditions. The stop-continue conditions are a mathematical or logical check that we define in our function in order to tell the function to continue or stop after we have handled the smallest piece of our problem. Without the stop condition, our recursive function will give nonsense answers or will go on forever, which we don't want. Now let's implement the factorial as a recursive function. We start with defining the function name and the input parameter. Here I have named the function fact, which is short for factorial. And I've also named the input number letter n, which is a variable. The large bracket marks where the conditions and calculations will be defined. Next, I add the stop and continue conditions. I will define the stop condition in order to stop the recursion when the input is 1. The continue condition is when the input variable is greater than 1. Please note that for illustrative purposes, I assume that the input numbers will never be a negative integer. Now let's add the calculations for the different conditions. So for our stop condition, which is when n equals 1, we calculate that the function should have an output of 1. We do that because we know that the factorial of 1 is equal to 1. But what about when our input number is greater than 1? Well, when our input is greater than 1, we will define the output of the factorial function as the product of n times the function itself with a parameter of n minus 1. So the fact that we're defining the output using the function itself means that we're using recursion. Notice that the parameter is 1 less than the original number. So here's another way of looking at the function definition I've created so far. Here I have two scenarios, the stop scenario and the continue scenario. Notice that both scenarios are handled by one function, the fact function. For the first scenario, we see that we have a certain input, a certain condition, and that condition being when n is equal to 1, and a certain output associated with that condition, the output being a value of 1. And for the second scenario below, we see that we have a certain input, a certain condition, and that condition being when n is greater than 1, and a certain output, and that output being n times the factorial of n minus 1. It's important to understand that both of these scenarios are using the same function. Now let's look at example input. If I give the function an input number of 1, the stop condition is triggered, and the associated output for the condition is produced by the function. In this case, the output for the stop condition is a value of 1. So as expected, the factorial of 1 is simply 1. Now let's look at another example using input value of 4. We start with our fact function and pass in a parameter of 4. That is, we pass in an input number of 4. Next, we check the input value against the conditions that we've set in our function. In this case, we trigger the continue condition since 4 is greater than 1. We calculate that the output of the fact function by substituting the value of 4 into variable n. And since the parameter for the inner fact function was n minus 1, we evaluate the parameter of this first recursive call as 3, because 4 minus 1 is 3. But in order to solve for fact of 4, we had to solve for fact of 3. We have called our fact function itself with a smaller piece of the problem. This action is called a recursive call. So now we have to set aside the first function, which was trying to solve the factorial of 4, and we have to take care of solving for factorial of 3. That is, in order to solve for the factorial of 4, we first have to solve for factorial of 3. We check the appropriate condition for the input value of 3, which results in another recursive call, and that recursive call is to solve for factorial of 2. So we make a recursive call for the factorial of 2 in order to solve for the factorial of 3. In other words, again, we have to set aside solving factorial of 3 and solve for factorial of 2 first. So we make the recursive call. Now, after testing the conditions for input value of 2, we see that we have to make yet another recursive call to solve for the factorial of 1. So we make that recursive call. Great. After 3 recursive calls and setting aside the functions factorial 4, 3, and 2, we finally reached our stop condition. What happens next? Well, in order to understand what happens next, let's simplify our previous diagrams. We started with a factorial of 4, but in order to calculate the factorial of 4, we have to call the factorial of 3. So we temporarily set aside calculating fact of 4 and calculate fact of 3. But again, in order to solve for fact of 3, we have to solve for fact of 2. So we temporarily set aside fact of 3 and calculate the fact of 2. But in order to solve for fact of 2, we have to solve for fact of 1. Yet again, we temporarily set aside fact of 2 and calculate the fact of 1. And so when we reach fact of 1, we finally reached our stop condition, which is when n equals 1. The stop condition means that the function produces an output of 1. That's how we've defined it. We take the output and return it back to its parent call of the fact of 2. The parent uses the value of the return recursive call and runs that calculation. The calculation is 2 times 1. So the factorial of 2 is 2. And we take that result, that output, to its parent call and give it to its parent call, which is the factorial of 3. The parent uses the value of the return recursive call and runs that calculation. The calculation is 3 times 2. So the factorial of 3 is 6. And return 6 to its parent, which is the factorial of 4. Finally, we're back to the original function, which is the factorial of 4. And the factorial of 4 is 4 times the factorial of 3. And as we determined, the factorial of 3 is 6, which we found using recursion. So our final answer is 4 times 6, which means the factorial of 4 is 24. A manual check of the factorial of 4 results in 4 times 3 times 2 times 1, which equals 24. So that means our recursive function gave us the correct answer. So that was a quick look at recursion. In the next video, I will talk about implementing recursion in JavaScript.